Right then. Good morning, everyone, and thank you for joining this round 3 discovery phase show and tell webinar. This one's about enabling future hydrogen pathways for industry. Next slide, please. So I'm Amy Oswin. I'm project manager and internal monitoring officer at the OFGEM Strategic Innovation Fund here at Innovate UK. I'm going to be introducing projects this morning that we're presenting in the session, but before we get into that, I'd like to give a little overview of the OFGEM Strategic Innovation Fund and our highlights to date. Next slide, please, Michael. So the OFGEM Strategic Innovation Fund is part of a 5-year partnership between OFGEM and Innovate UK, UKRI, and that's to deliver energy network innovation with the vision of accelerating the UK's transition to net zero at lowest cost to the consumer, and to make the UK the best place for energy businesses to grow and scale. We're aiming to make the UK a global hub for energy innovation and focus our purpose across 3 core areas, which are people, planet, and business. Next slide, please. So to achieve our vision and fulfill our purpose, we issue 4 annual innovation challenges across 3 stages of funding. So we have Discovery, which is a feasibility study, Alpha, which is proof of concept, and Beta, which is the full demonstration, with a focus on alignment, diversifying the pipeline, responsiveness and commercialization, which in turn allows the OFGEM Strategic Innovation Fund to fund truly transformational projects and generate an incredible amount of evidence and insights. Next slide, please. So through these funding opportunities, to date, we have so far supported 201 projects and awarded over £136 million in funding. And an early indication of the benefits generated by these innovations is an impressive potential cost saving of more than £2.6 billion by 2035. And we're only halfway through the programme. Next slide, please. So for round 3 discovery, 53 applications were awarded funding, and today's show and tell session is to demonstrate what's been achieved by projects in the enabling future hydrogen pathways for industry space. As we transition towards net zero, the need to decarbonise presents new challenges. And whilst electrification is often the most accessible option, some scenarios require hydrogen as an energy vector. And although hydrogen's versatility makes it valuable, it also creates challenges in identifying the best pathways from production to end use. And as a result, versatility of innovation is necessary. Different types of innovation can be seen across the sector in the form of new policy and regulation, new business models to create market and demand, the deployment of new infrastructure, and the development of new hard and software. All of this leads to positive environmental impact whilst creating economic benefits, not just through new markets, but by preserving skills and expertise developed in the oil and gas sector. The projects today cover a suite of hydrogen innovation with the potential to accelerate our shift to net zero. Next slide, please. As you can see from the agenda, we've got 4 projects presenting this morning, and each one will be giving a 10-minute presentation followed by a 5-minute Q&A. If you've got any questions for the projects, please do type them in the Q&A box, and we will endeavour to answer them all during the Q&A section. But let's get started with our first project. Next slide, please. So the first project to present today is carbon and hydrogen transportation to SAF production facilities and is led by National Gas Transmission PLC. And I will hand over to them now. Next slide, please.
Brilliant. Thank you very much, Amy. Good morning, everyone. So I'm Matt Hammond. I work in the innovation team at National Gas Transmission, and I've been the innovation lead on this SIF Discovery project. If we can skip to the next slide, please. Brilliant. So this first slide just gives an overview of what NGT, National Gas Transmission, do today. So we own and operate the high pressure natural gas transmission system in the UK. So we take natural gas from terminals along the coast, so up at St Fergus, and also LNG terminals down in Milford Haven in the Isle of Grain. We take the gas from the import terminals and transport it across the country through a system of high pressure pipes. we essentially deliver gas to the distribution network, so the likes of Cadent and Wales and West, etc., who then deliver it onto homes and businesses via the local distribution networks. We are directly connected to some users, so large industrial users such as steel mills and paper mills, and also power generators as well. So I think we're connected to around about 40 or so natural gas-fired power stations. So that's our current network today. So if we can skip on to the next slide, please. Brilliant. So this is what we're looking to do in the near future. So we're looking at converting a large portion of our network to hydrogen and transport hydrogen. So that's sort of twofold. So we've got Project Union, which is our flagship hydrogen project, which is looking to convert around about a quarter of our existing network to carry 100% hydrogen from production sites, major production sites, to the large demand users. We're also looking at blends of hydrogen and natural gas, so in the rest of the network, to enable sort of the scale up of hydrogen production and be able to sort of transport it to key users as well. On the other side of things, we're also looking at how we can interact with carbon capture. So can our network be used to transport carbon dioxide from, again, the large industrial clusters where there's a lot of CO2 generation to things like storage sites. So I think we can skip on to the next slide, please, and just start to introduce the project. So this project is looking at sustainable aviation fuel and how our future networks, so hydrogen and carbon dioxide, can actually support sustainable aviation fuel production in the UK. Aviation is responsible for a good chunk of emissions in the UK today, and obviously the sector has a lot of things going on looking to decarbonize that. So things like aircraft efficiency improvements and also alternative fuels such as hydrogen and batteries. However, sustainable aviation fuel is starting to kick off and is seen as a big sort of enabler in terms of getting aviation to net zero. So over the next few years, we're going to start to see sustainable aviation fuel production starting to come online, and through to 2050 and beyond, SAF is going to play a big role in sort of the airline sector and reducing emissions. So SAF is very similar to conventional fossil jet fuel, only it's obviously synthesized. So a lot of the existing infrastructure can be used to transport and handle and distribute SAF that is used for conventional jet fuel today, which is very handy. Currently, SAF can be blended with fossil jet fuel to work in the engines up to certain blends. However, 100% SAF certification is sort of being developed as well. There are a number of methods to produce SAF, and some of these use hydrogen and or CO2 as the feedstocks, which is where our interest and this project sort of comes in. So availability and cost of these feedstocks is going to be key to sort of accelerating growth of SAF in the UK, and that's where I think this project can help. So on the right hand side, we've got some potential benefits that I'll just whiz through that we've identified. So currently SAF production is looking at on-site production of hydrogen and carbon dioxide where it's needed for the processes that need those feedstocks. However, if you connect to our networks in the future, you could actually avoid the need for this kind of on-site production, reduce your plant footprint, and ultimately your capital costs as well. We could also provide some flexibility in terms of where SAF is produced. So if we have a network that's running up and down the country, which is transporting your feedstocks, theoretically you could jump in anywhere on our network and produce SAF, which could provide some benefit in terms of the flexibility there. Network connections offer sort of increased security of supply versus saying having a single electrolyzer on your site. You're no longer relying on your hydrogen supply coming from that electrolyzer and your storage system. You're connected to a network, so you're essentially tapping into a number of sources of hydrogen. Same for CO2 as well. Potentially, the efficient nature of pipeline transportation of gases could reduce the costs of hydrogen and CO2 compared to that on-site production, and that ultimately propagates through to your fuel costs as well. So ultimately, what we're trying to do is accelerate the production of SAF in the UK by enabling these network connections. So we can skip on to the next slide, please. So this, just very quickly, I'll go through the scope of what we covered in Discovery. I think the key bits were kind of the benchmarking and literature reviews carried out by Bath University, or University of Bath, sorry. They provided us a good idea of what the demand of CO2 and hydrogen is going to be for the various different methods of SAF production, and also where our network could sort of support there in terms of the volumes of hydrogen and CO2 that are going to be required. The next key bit, I think, was the concept design for a SAF production facility where you're connected to a network. So understanding what that potential facility could look like and trying to compare that to the current state of the art. And finally, we looked at a gas network connection design. So what would that need to look like, and what do we need to know in order to design a site that could provide the feedstocks for a SAF production facility? Just at the bottom there, the work package 5 was stakeholder engagement. I feel this was quite an important part to this project, and it was very useful to be able to reach out to the key players in the aviation industry and understand their needs and where they think the SAF industry is going to go. If we can skip on to the next slide, please. So we work with quite a few partners on this project. So we're the lead network on this one, and Wales and West are the distribution network for Wales and the southwest of England. And they've done a big study on hydrogen for aviation very recently, and it was good to tap into their learnings from that. As I said, University of Bath did the sort of literature reviews and benchmarking. They've got good technical knowledge on SAF and alternative liquid fuels, as well as hydrogen. Premtech are one of our framework designers. They do a lot of design on our network today. They're also working very closely with us on our net zero innovation project, so the hydrogen and CO2 as well. They also have experience in the fuel product pipeline side of things as well, so that's very handy. Airbus and Rolls-Royce are very much interested in SAF and have a big presence in kind of the SAF industry and good knowledge. So they were supporting partners, but it's very useful to get their input on what we're doing. Likewise, Sustainable Aviation, headed up by Andy Jefferson, is a large consortium of partners from across the aviation industry. So it's very good to be able to tap into the contacts there and also Andy's experience. And I'm very pleased to see that he joined the call. So I think I can hand over to him, and on to the next slide, please. Thanks, Andy.
Thanks, Matthew. Can you hear me okay?
All good, yep.
Oh, okay. Apologies, I'm in a station waiting room, so there might be some background noise, but I'll keep it as quick as I can. So just to share the sort of, or add context, I suppose, to what Matthew said, this is the UK Aviation Decarbonisation Plan published by the industry in April 2023. And the most important thing, I think if you can just click on one, it'll just highlight the sustainable fuel potential here, which is that 39% wedge. So basically, the largest opportunity to reduce emissions from UK aviation and to hit our net zero target commitment by 2050 comes from, slide please. And on again. So go to the next slide, please. So as Matthew's saying at the moment, we're mainly looking at first generation use cooking oil. So if you go back a slide, please. So the main area where hydrogen is going to give us the greatest benefit is in generation 3, which is the e-fuels power to liquid, where we're combining hydrogen with captured carbon and using renewable energy. But actually, there is also a reasonable amount of hydrogen that will be required in our second generation fuels as well, as part of the processing of turning wastes into sustainable fuel. So in both second and third generation, we've got an opportunity to be using that hydrogen supply. Moving on to the next slide, please. So this was the latest economic analysis of the job and GVA potential for the UK by 2050. So this was done by an independent company called ICF. And as you can see there, there's a complete UK coverage opportunity for sustainable aviation fuel. The UK government are supporting SAF development in the UK through what they call the Advanced Fuel Funds. So those are the sort of orangey yellow diamonds on the map that span across the country. And then where we've got effectively a refinery site is where we think probably most SAF production will take place, with effectively feedstocks, be that hydrogen or waste or other things, being directed to get to the refinery site for processing to turn into sustainable fuel. Exactly how those facilities roll out will be due to how competitive development occurs, but effectively the job of GVA ranges that you see in the chart are our kind of latest best guess of how we think we're going to get to that position of 60,000 jobs and £10 billion of economic value from the UK producing and selling sustainable fuel by 2050. Go to the next slide, please. So just reinforcing that point, the UK government have recently published both a SAF mandate decision, which is what this is, but they're also consulting at the moment on what they call a revenue certainty mechanism. It follows a similar pattern to the government's work to encourage renewable energy development with offshore wind a few decades ago. So what they've done with the mandate is set a minimum amount of sustainable fuel that the aviation industry need to be using. So the figures relate to the percentage of sustainable fuel as a total of the UK aviation fuel demand. So we go up from 2% next year to 22% by 2040. And effectively the PTL obligation is that kind of key piece around the hydrogen supply. So we're expecting a reasonable amount of hydrogen supply from 2030 growing ever more onwards as we go forwards to provide that power to liquid fuel. And I think maybe one more slide if you click on. No, that's me done. So I will hand over to well, back to you, Matthew, maybe, and then across to Brent. Thank you.
Yeah, I think we've sort of eaten through our presentation time a little bit, so apologies for that. I think I spoke for too long at the start. I don't know if it's worth, Amy, us skipping straight to the Q&A, because I've seen a few questions come through. Apologies, Nick, as well.
Yeah, no problem. Yeah, we have had a few questions in. So firstly, the SAF mandate acknowledges that the targets will likely require imports as well as domestic production. Is this accounted for in the demand forecasts, and what implications does it have for your system design?
So on the first side of it, I think we're obviously aware that a lot of it will need to be imported. What we would kind of hope to show in maybe a best case scenario is that we can actually support the SAF industry in a way that we can actually reduce the reliance on imported SAF. So can the physical volume that our networks can deliver to SAF production facilities actually scale SAF production enough in the UK that we can avoid or reduce our reliance on imports, which would be great, obviously. On the system design side of it, I guess there's enough separation in terms of where our network would connect to SAF production versus what a SAF import kind of system would look like. So I can see that being quite separate, and I don't think it would have much impact on our design, given we would be directly connecting to a single SAF production facility, which would then send its SAF on to wherever it needs to go. Andy, I don't know if you can jump in on that one as well.
Yeah, I think that's right, Matthew. I mean, basically, yes, there'll be an imports. The imports will probably be the heifer use cooking on SAF. It's the UK government's intention for that to be minimised as much as possible. So it feels like as quickly as we can scale domestic production of SAF and the use of hydrogen in that. That's what the government's looking for, and certainly the industry is happy to work with that too.
Fantastic, thank you. I'm really sorry we've run out of time, unfortunately, but for those of you who've put questions in that we haven't got to, we will be able to answer those offline if you can let us know directly who you are, and then we can get the response out to you. Thanks very much, guys. And we are now going to move on to the next presentation, which is also National Gas Transmission, but it is HyNTS Maritime. So can I hand over to the National Gas Transmission team, please?
Hello. Yes, hi, lovely to be here. Next slide. Yeah, okay, brilliant. Thank you all for this opportunity to present. I'm presenting the HyNTS Maritime project. I'll be presenting with my colleagues Jamie from OFGEM SIF and James from WSP. Next slide, please. So just as a context overview, we've got a project overview of what we're going to be doing. Next bullet point. The activities that we did in each work package and what we found out from them. And then finally, what the project outputs were and benefits looking forward to the future, and generally what our plans are for the future. Okay, so I won't go through all of the project partners, but you can see we've got a lot of different project partners with a real variety. So we've got consultancies that helped us with the feasibility and business case. We have the technology providers that provided insight into our hydrogen carriers. We have people that have worked on different projects that are similar to this, and we also have a port authority that gave insight into our ports in the UK. Next slide, please. So the interface for this project was to really bring sort of the key stakeholders together to understand how we could deliver this project, which I'll explain in a bit, and determine the feasibility, whether we could even do it in the first place. Alpha will be designing the demonstration and making sure that we can really do it from a strategic cost-benefit analysis. And then Beta will hopefully be a full-scale demonstration to deliver this in the future. So the project is, next slide, please. So our main focus on this project was importing hydrogen through hydrogen carriers via ships that would eventually go onto the national transmission system, but also potential early off-takers as well. So essentially we were looking at that as a primary thing for energy resilience, but also optionality for the consumer when it comes to green hydrogen. We also looked at different sustainable alternative fuels for the maritime industry, and maybe this will feed back into how we make transporting this kind of thing, like hydrogen carriers, more sustainable, but also the idea that potentially one day we could also export hydrogen through hydrogen carriers. Next slide, please. So our proposed scope was work package 1 was project management, work package 2 we were developing out the business case and our requirements. So essentially looking at what kind of volumes we could potentially be seeing, whether there was a real business case behind it, what the feasibility of this was like. Also looking at different ports and considering their requirements and how sustainable it was as well. Work package 3 was our technology one, so it was looking at all of the different hydrogen carriers and understanding the advantages and disadvantages of using each one. So looking at ammonia, looking at metal hydrides, looking at methanol, and understanding really the techno-economic analysis of this and comparing and contrasting them. Work package 4 was looking at how it would connect up into our system, whether we needed sort of early off-takers, a standard design for it. And finally, work package 5, an incredibly important work package, was our stakeholder engagement. So really understanding where we needed to engage, reaching out to people, and understanding in the future where was important that we needed to engage in order to make this a reality. Next slide, please. So I'll hand over to James Watt now, who's going to go through work package 2.
Good morning. So work package 2 was effectively focused in on the maritime issues and the port issues. There was a significant amount of demand forecasting and understanding what the maritime fuel debate would be as well, because it's important to understand if ships bringing the importation in can use the cargo as fuel. So it's a mapping of potential demands, and more importantly, a mapping of potential ports, because it was widely felt that not all ports are created equal, and an assessment needed to be made to understand where and when imports can be brought in from a point of view of what the facilities can handle, whether it's appropriate to bring large volumes of ammonia, for example, into some ports, and the connectivity into the national grid. If you are bringing in ammonia or bringing in hydrogen via another energy vector and cracking it back to hydrogen. In terms of Work Pack 3, because it's run straight on, it was multifaceted. Effectively started looking at the technology types for the handling of the energy vector, particularly ammonia as a hydrogen carrier, and examined an alternative, which was a relatively moderate TRL non-organic hydrogen carrier mineral in an oil, to understand what the demonstration phase of the project might look like. Considered all the costs, cracking the different technology options, and there's lots of options available for transport by ship and for getting into the network, but they start into the realms of needing them to be demonstrated, and that will be the focus of the project going forward. Next slide.
Great, I think it's, my slides now, so thanks, James. So GEMSIF's role in the project was really looking at two elements, so the techno-economic analysis and also the stakeholder engagement. So starting with the techno-economic analysis, we looked at 4 different carriers, so ammonia, methanol, DBT, and magnesium hydride suspended in oil. And we were really assessing the cost of transport. So this is shown on the figure on this slide, so taking low carbon hydrogen as an input to the model, and capturing the costs of carrier production, carrier export storage, shipping the carrier, import storage, and reconversion back to low carbon hydrogen. So this was assessed using a discounted cash flow model, and to calculate the levelized cost of transport of the carrier. You can move to the next slide, please. Great, so in terms of the results, based on this early stage assessment, we think that ammonia is likely to be the lowest cost carrier when utilizing H2 sites cracking technology, and that's really due to the high efficiency of the cracker. But if ammonia isn't a suitable option due to health and safety or environmental challenges, or H2 sites technology doesn't perform as expected, then we think magnesium hydride suspended in oil is likely to be the most cost competitive carrier. The cost of magnesium hydride suspended in oil increased more quickly with distance, and that's shown by a steeper line on this graph. And that's due to its lower hydrogen content than other carriers, requiring more or larger ships for the same volumes of hydrogen. Great, and now if we can move on to the stakeholder engagement slides. Oh, sorry, they're not yet.
No, back to me briefly, and this just follows on to what I said in the earlier slides. And one of the things we see not having been done before is the ports assessment, where you can bring large volumes of LOHCs, NOHCs, ammonia, whichever, into the country, and assessing the connectivity into the network. Some ports do not have ready access to high pressure pipelines, so that has an impact, because you'll have to run those lines as part of any import project, and they're expensive. And just as importantly, planning for new pipelines is an extensive process. So we just did a port by port, matched the port assessment that was done by our Maritime team, and we ran it through our gas and hydrogen team, to understand where it can connect, and then understand the mechanisms for which it does connect, and how difficult it would be. There's a fairly well-established connectivity process for the national gas network and the distributed gas networks, which seems robust and no different from if you were importing LNG. And connection design is well established, but it's also part of another national gas project that we're doing for imports into the network from any hydrogen source. So it was quite clear from the assessment, wherever we go, it's doable. it's more a case of costs for some of the ports would be more disadvantageous, or a bigger disadvantage for some ports than others. As the next slide.
Great, so back to me. So work package 5 was looking at stakeholder engagement. So we engaged with 8 stakeholders so far as part of the project, and that included GDNOs, 4 port authorities, SSE, and Ikigai Capital. And we're still looking to engage NGN, Wales and West Utilities, the MCA, and HSE as part of the discovery phase. And have begun some work looking at the alpha phase stakeholders that we'd like to engage. You can move to the next slide, please. So some of the key takeaways from the stakeholder engagement: regulation was consistently mentioned as a key enabler for hydrogen import, and the suitability of ammonia was a major topic of conversation. So particularly from a health and safety perspective, but also power grid connection, location, and storage requirements. In terms of knowledge of different carriers, ammonia was the most well known, followed by e-methanol, LOHCs, and there was generally a relatively low level of awareness around metal hydrides. Something that we thought might be quite important is, something as James mentioned, is citing a demonstration project where ammonia trade already exists. This is due to kind of safety and regulation aspects already being in place. And this was validated within the stakeholder distribution network.
Next slide, please. Okay, so the main project outputs was there is a really strong business case for importing hydrogen via ships into the UK. So there's a huge demand that is yet to be filled really by hydrogen production in the UK. So it's likely that we will need to have supplements for that energy resilience into the UK and also to create that UK hydrogen liquid market. So it's definitely a necessary project to have. We sort of narrowed down both the technologies and the port selection and will continue to do so within Alpha. Our stakeholder engagement as well was vital really for this piece of work, and we will be continuing to engage with our different stakeholders within Alpha and in the future. Next slide, please. So the main project benefits are enabling energy resilience for a future UK energy system. At the moment, National Gas our network does take imports, it does take different sources of natural gas, and it's crucial for that energy resilience that we have this really in place, tackling that consumer vulnerability. It also keeps the optionality for consumers on where their energy comes from, whether that be a cheaper energy source or a greener energy source. It increases the speed at which the UK can enter a liquid hydrogen market, and hopefully, because there would be potentially a solid supply of hydrogen, it would mean that other projects with hydrogen would be able to commence. With that, it would create more jobs at ports and within this industry, and enable the UK to reach its net zero targets faster. And eventually, it would hopefully open the door for the ability to eventually export its own green hydrogen through the same process, but to other countries, if we were ever in a place that we were producing more hydrogen than we were using, like we do currently with natural gas to Europe. And that's it. Thank you.
Fantastic. Thank you very much. We have had a few questions in. So firstly, for the lower TRL fuels, and Mineral Tech was mentioned, will there be work done in further work packages to understand their viability and or help these fuels move up the TRL scale to more accurately assess their potential?
Actually, no. So we did look at it as a potential option, but the reality is that we won't be able to do that within the alpha phase, just because of the sheer amount of work we need to do in terms of trying to find out whether it's even feasible. So we will actually be looking at a ammonia, green ammonia, with H2 sites technology and alpha phases in the future. But it's definitely a really good question, and I do think that potentially it has room in other projects, but just unfortunately with how we're having to move at pace realistically, we've had to make some judgment calls on what research was done in this discovery phase, and at the moment it's ammonia through H2 site that has technically the most potential at this point, but that's not to say that the other technologies won't be investigated in the future.
And just another quick one before we move on. Hydrogen carriers are important vectors, but how do they compare over life cycles with compressed gas and liquid hydrogen?
So I don't know, Jamie, whether you looked at this on your technical analysis, but if not, I can.
Yes, we didn't. We kind of descoped it initially. If it's talking about cost here, I don't know whether they're talking about cost or emissions because they mentioned life cycles. But in terms of cost, we think for longer distances, kind of liquid or compressed gas is likely to be much higher cost than carriers. I think for shorter distances, liquid and compressed gas can make sense. We think the cheapest renewable energy and therefore the cheapest green hydrogen production is likely to be kind of longer distances away. So we thought carriers are probably more appropriate things to test the cost of for this project.
Fantastic, thank you. Unfortunately, we're out of time, but if you, the project team could answer those questions in the background, that would be useful. And we're going to move on to the next project. So the third presentation is on advanced low carbon hydrogen and energy management, and that's led by Wales and West Utilities Limited. So I'll hand over to the project team for their presentation.
Great, thanks, Amy, and good morning, everyone. So I'm Henry from Wales and West. For those of you who don't know me, I lead our industrial cluster portfolio of projects. I just want to start by saying that much of the work that we've undertaken with industrial customers has demonstrated the need for hydrogen in the next 5 to 10 years, if not sooner. And in particular, we see the need for co-located hydrogen production and use in dispersed clusters, so outside of the main industrial clusters, and as well as that in a network where hydrogen in the grid might not be available at such an early date, and therefore industrial customers need hydrogen sooner. So we're already seeing early projects develop through the HAR1 and HAR2 process. Many of these are hampered by a lack of grid connection, which limits the projects which can feasibly go ahead on time and on budget. And this fundamentally is why we chose to embark on the Advanced Low Carbon Hydrogen Energy Management Project, or ALCHEM, which uses Key Hydrogen's proprietary biomass electrolysis technology, which in turn uses less energy than traditional PEM or alkaline electrolyzers. So I'm going to pass over to Koji, who's going to run you through the details of the project, and then I'll come back at the end for Q&A. Next slide, please.
Perfect. Thanks, Henry. So my name is Koji. I'm the co-founder and CEO of Key Hydrogen. The main three partners we had for this project was, of course, ourselves, Wales and West, and then we also had HyNTS, which is part of the EDF group. So they're kind of the hydrogen focused part of the group, and they were able to provide really good insights kind of on the industry perspective, because of course they're involved with quite a bit of hydrogen production, project development activities. Next slide, please. So this is a quick overview of the agenda that we'll be going through. So starting off with some initial roles and responsibilities, scope, and then we'll essentially be stepping through each of the 5 different work packages that we completed for this discovery phase, and then talk about next steps. Next slide, please. So as Henry mentioned in the beginning, so we had Wales and West as the project lead, Key Hydrogen as the project partners. So we led the deliverables, and then we had HyNTS involved as well. Next slide, please. Sorry, yeah, perfect. So in terms of this project, we were looking within the specifically competition scope of enabling power to gas to provide system optimization. And the overall objective was to demonstrate the commercial feasibility of our novel biomass electrolysis technology. So we can produce green hydrogen and green chemicals from liquid biomass waste. And the two big advantages, we use less energy than kind of what's theoretically even possible through water electrolysis, while also producing a useful chemical co-product that we can sell. And both of those combined help reduce the cost of green hydrogen production. And really, at the end of the day, this is really just looking at how can we reduce that cost of hydrogen production as much as possible to make it economical. Next slide, please. So just a quick overview on our technology approach. So this stems from our CTO's research at the University of Cambridge. On the left, you have the standard water electrolysis approach, where you use renewable electricity to split water into hydrogen and oxygen. Our kind of completely different approach is, rather than taking water as our feedstock, we're taking liquid biomass waste. So in this example here, it's kind of this side stream from woody waste. And by directly electrolyzing it, what we're doing is we're changing what we're actually oxidizing. So we're no longer directly oxidizing water and producing oxygen. We're breaking down the biomass, producing these chemical co-products, liquid chemical co-products that we can separate out and sell. So you can see on the right hand, on the anode side, we're actually no longer producing oxygen. So there's no bubbles, whereas on the left hand side, you still see the bubble formation from the hydrogen. Next slide, please. And just what this would look like at scale, we're envisioning kind of an on-site pilot where we can work directly with, let's say, a brewery or a paper manufacturing company. We can take their waste, produce the hydrogen directly on site. And these are the same companies that are looking at using hydrogen as a decarbonization vector to decarbonize their core operations. Next slide, please. So the 5 deliverables, the first 2 were really around kind of this customer discovery, stakeholder engagement piece. So looking at one side, which is just the waste biomass providers, looking at availability, what's the most suitable waste streams, and then on the other side, the off-takers, and seeing who's actually would be interested in this hydrogen and co-product offtake. Then we did a quite thorough techno-economic model to assess, is this technology actually going to be cheaper than standard, water electrolysis? We looked at competitors, emerging competitor technologies, and finally the risk registry around commercialization. Next slide, please. I think you skipped one. Perfect. So we held customer discovery calls with 20 different companies. Very important for me to highlight here that these do not represent a partnership by any means. They're just happy to kind of take a conversation and interview with us. And of these 20 customer discovery calls, 8 of them were quite interested in the technology and have actually sent us kind of their waste samples so we can further test them in our lab facilities. The kind of big outcome out of this whole discussion and talking of all these different industries is, from an initial standpoint, what we think is the most interesting feedstock is this non-recyclable paper waste. So when you recycle, let's say, cardboard, and the UK actually does quite a good job of recycling cardboard, kind of 80% recycling rate. You can only recycle it a certain number of times, like 4 or 5 times, because every time you recycle it, the fibers get shorter and shorter, and they continue to lose strength. Eventually, they naturally fall out of the recycling process because they can't be recycled anymore. And that it's a cellulose-rich side stream that currently actually does kind of go to either land spreading or landfilling. And there's quite a lot of this generated in the UK and the EU. And so we think this is a perfect kind of initial waste stream that we'd be targeting. Next slides, please. And on the off-taker side, so again, these do not represent partnerships, just companies that were happy to speak with us. The most kind of interesting opportunity we saw here, because for these initial, demonstrations and pilots, we'd be producing small amounts of hydrogen. So National Gas Metering actually has this kind of operating demo kitchen, hydrogen kitchen, which they're using for combustion purposes. So, we're not necessarily saying this is the best long-term use of hydrogen, but in terms of what's actually being used today in the market and the interest for green hydrogen there, we think it's a good starting point. Next slide, please. So this is kind of the in-depth look at how much does it cost us to produce the biomass electrolysis hydrogen approach. So we're pegging it at kind of 1.7 pounds a kilogram at scale. You might be familiar with UK HART1, kind of the strike price was agreed around £8 a kilogram. So, today's hydrogen production is quite expensive, and we're well aware, but just to put this on an apples to apples comparison, the business as usual water electrolysis uses the same kind of assumptions and fundamental, CapEx and electricity prices that we're looking at. So even on an apples to apples comparison at scale, we see ourselves, being less than half the cost of water electrolysis. So, what does that mean to consumers? Well, the UK has this kind of 5 gigawatt target of electrolytic green hydrogen by 2030, so in total 10 gigawatts. So, producing that through standard water electrolysis is going to cost close to £2 billion per year, every year, to produce this amount of green hydrogen. We feel we can save, if we were to produce all that hydrogen instead using this biomass electrolysis approach, we would be directly saving about £1 billion a year. So quite significant, especially in the context of what the UK aims to achieve. Next slide, please. I recognize going a bit over, so we'll go quickly through these. Again, just looking at a couple different competitor technologies, but the main differentiator for us is the only gaseous output is pure hydrogen. All the carbon stays in liquid form. We're not combusting the biomass, so there's no toxins or pollutants. We don't need this kind of further gas separation, gas treatment step, because we're just going directly from waste to pure hydrogen. Next slide, please. And then, we did, of course, identify a lot of different commercialization risks. These are just highlighting the kind of high impact or high likelihood risk that we'll be targeting. Next slide. And then just talking about in terms of how do we continue on evaluating this technology, the two main aspects: technical, scaling up the technology, engaging a lot more closely with these stakeholders, and then on the commercial side, starting to look more in depth at the next on-site pilot, and talk about securing feedstocks and offtakes and that financing strategy. So that's the end of the presentation. So happy to switch over to Q&A.
Thank you so much. Yes, we do have a few quick questions. So can you use solid biomass in your electrolysis process if it's processed to become liquid?
Yes, we can. So actually most biomass, even if it is solid, they have quite high moisture content. And that's actually a challenge with most conventional uses of biomass. So just burning it, of course, the more water content there is, it requires a lot more energy to burn that. Whereas for us, that's a benefit. So we do have a pre-treatment step depending on the type of biomass that it is. So even if it starts off liquid, it'll probably have good moisture content. We'll have a pre-treatment method to kind of break that down, solubilize it, homogenize it, to eventually feed into our process.
And what are the typical byproducts that you generate?
So they're kind of short chain carbon acids, things like acetic acid, formic acid. And those are commodity chemicals that today are derived from fossil fuels. But we are not, on the techno-economic model, we're looking at just selling them at base commodity price. We're not looking for a green premium there. But it's also another avenue that we're actually decarbonizing the chemicals sector as well, because this carbon, of course, is now being biogenically sourced as opposed to be from fossil fuels.
Okay, and would the biomass electrolysis approach work on wastewater?
Potentially. So we can use quite a bit of the feedstock is lignocellulosic biomass, so quite a broad range. We did look at wastewater. We won't start there because it is a bit more complex in terms of you can have different kind of toxins and different chemicals that end up in that wastewater. It just means a lot more upfront pre-treatment to make it suitable for the process. Again, it's possible, but to demonstrate the technology, we'll be starting with these kind of easier, to process feedstocks, and then we'll look at expanding that scope.
Thank you. One of the attendees has put a link in the Q&A as well, just for some additional information. But thanks very much. And I think we'll move on to our fourth and final presentation for today. So next slide, please. The final presentation is Look North 2, and that's also led by National Gas Transmission PLC. So yeah, now we'll hand over to that team.
Hi, everyone. Just waiting for team members to join. Alistair, we can't hear you.
Hi, Alistair. Is your audio muted on your computer? Okay. Alistair, I'll try and reach out to you via the chat to try and troubleshoot this, potentially if somebody else can take over for the time being. Thanks very much.
Yeah, sure. I can get us going anyway. Lovely to meet you all. So as we said, Look North H2 is a piece of work that was done and driven by National Gas Transmission, but we've had some great partners in the SO, and we've worked with a number of stakeholders as part of the engagement. I'm going to hand over to Sava and Mo, who are going to take you through kind of the key findings that we have got from the presentation, and then I'll kind of wrap up before I hand over back to you, Amy. So Sava, let's jump straight in.
Yeah, I guess I'll take you through the outline of the project really quickly. So first we're going to present the background and problem statement, then do some presentation of our high-level project outputs, and then Imran will take you through the next steps. Imran, if we can go on to the next slide. Yeah, so what is Look North essentially? Our problem statement really states that creation of offshore energy hubs could further stimulate the deployment of UK offshore wind and support the development of a hydrogen economy. The concept has been trialed in other countries. However, it is still yet uncertain what are the benefits and costs in developing offshore energy hubs for the UK, energy transition and energy security, and what are the commercial models and market designs that we need to successfully integrate offshore energy hubs into the whole kind of energy system, and most importantly, what level of coordination would be required between the UK and other European countries on codes and regulations to enable the development of this cross-country offshore energy hubs. In terms of our deliverables, we have produced 6 work packages, starting with data collections that ultimately we used for production of our CBA, and then we did the in-depth market and regulatory gap assessment. And obviously, the pearl of our study is a stakeholder engagement. where we have engaged with a variety of stakeholders from different industries, as well as governmental bodies. And yeah, and we look forward to successfully integrate all of this into our alpha application in the end of it. On to the next slide, if possible. So just briefly touching on some stakeholder engagement that we have conducted. So obviously, yeah, a lot of stakeholder engagement with networks that included National Gas Transmission, ESO, National Grid, GasUME, industry partners such as Ørsted, National Energy, Eni, and policy and regulation partners such as DESNES and the Crown Estate. Now I will actually go into the actual findings of the study. If we can go on to the next slide. Yeah, thank you. So yeah, I'll start off with presenting the archetype of the concept for the offshore energy hubs. As you can see from the drawing on the left, in the business as usual scenario, we do assume that the offshore wind clusters to be connected to the shore by a decentralized way, where each cluster has its own connection to the shore. The hydrogen production takes place onshore using the electricity that is being supplied by the offshore wind, and the carbon is being sent from the shore to offshore in order to be injected in the reservoirs, therefore leveraging the oil and gas rigs for the injection. On the right side of the slide, you can see that our Look North concept, a concept that explores the repurposing of oil and gas infrastructure for both hydrogen production and carbon capture. The main difference of our concept from the business as usual is now that the offshore wind clusters are being first connected to the offshore hub that is developed between the clusters and the shore, and then the electricity is sent to the shore using a centralized connection. The hydrogen production now occurs offshore through locating electrolyzers on a constructed offshore platform that is collocated to the existing oil and gas rigs. The produced hydrogen is then sent to the shore, leveraging repurposed gas pipelines in close proximity. Look North really creates this vision for a more optimized approach to production and transportation of energy. And this comes through optimizing energy production, which is key to achieving the 2050 net zero targets at the lowest cost for consumers. It is important, as UK is set to rely on offshore wind for most of its final power and energy use. And with that, a centralized offshore energy hub concept may be able to provide significant socioeconomic and environmental benefits by integrating use cases, and on which I will touch on the next slide. Thank you. So based on the conducted detailed cost and benefit analysis, the conclusion has been that all hub configurations and zones do report financial benefits, with most of these benefits occurring when the hub is developed further from the shore. A bit more context on the defined zones, as in the early stages of the project, we have determined the 3 most applicable zones in the UKCS region based on the parameters such as close proximity to the existing energy infrastructure that the hub could leverage, as well as others. And now onto the actual benefits. As it can be seen from the graph on the left, most benefits are provided at zone A, which is further away from the shore than both zones B and C, by actually almost twice of distance. It is important to note that these benefits shown are for 15 gigawatts of connected offshore wind, which represent 15 different offshore wind clusters with 1.5 gigawatts capacity for each cluster connected to the hub. Our analysis has been conducted at different capacities, ranging from 1.5 gigawatts to 15 gigawatts, and at 15 gigawatts for zone A, it resulted in the biggest benefits of over 10 billion cumulative discounted net financial benefits by 2068, and this assumes 45 years of the lifetime of the project. The majority of the benefits came from the infrastructure optimization, followed by energy losses reduction, and with that, the monetized CO2 emission reduction savings. Other benefits include curtailment reduction and platform decommissioning savings. And most importantly, of course, the provided benefits do come at an additional cost, as over £1 billion will need to be invested in the hub development, and this mainly is for the construction of the actual platforms. Apart from the financial benefits, the hub could also provide significant environmental and societal benefits by reducing more than 9 megatons of CO2 and maintaining or creating 3,740 jobs. That's all from me. Now I'll be passing on to Mo to walk through the regulatory and market design components of the study.
Thanks, Siva. If you move on to the next slide, please. So to ensure that the benefits my colleague has just gone through are realized, there are key gaps surrounding regulations and market design that must be plugged. On the regulations piece, which I'll be starting with, we started off with really understanding what offshore energy hub regulations should cover, and then through stakeholder engagement, we evaluated the current regulatory landscape. Here we discovered the major problem was that the regulations were highly fragmented and siloed by sector. And while we also recognize that there's work being done in the current regulatory landscape, we recommended that there be increased clarity on approvals and timings, and more importantly, a sort of regulatory sandbox to enable early stage system integration projects. Finally, we gave a few directions on what future work we'll need to focus on. I'll move over to the next slide, where the bulk of work focused on. Now, next on market design. To analyze market design of offshore energy hubs, we created a framework that encompasses multiple areas. Now, for the first one on market arrangements, we explored different sort of trading arrangements like offshore bidding zones versus a home market setup. And ultimately, we based our assessment on what an OBZ arrangement could be like for both the offshore wind farm developer and also the hydrogen off-taker. Then next, we evaluated what balancing and operability of offshore energy hubs entail by assessing what balancing options exist currently and the potential savings hub assets can provide through ancillary services. We also looked briefly at how the hydrogen off-taker could provide flexibility by fluctuating his outputs. Next, we explored what the interaction with EU markets will entail and what kind of planning will be required. We started with really defining what the joint target of these North Sea countries were, and then provided recommendations to realizing these targets. We also assessed specific technical and commercial aspects, such as the different capacity allocation and calculation methodologies. We recommended what should be considered when designing a network charging methodology as well. And additionally, we assessed the CFD mechanism and also thought about how that would be affected in an OBZ scenario. And finally, we evaluated contractual arrangements. We dove a bit deeper into key factors to be considered when developing any codes and contractual arrangements for offshore energy hubs and its assets. That's it from my side on the regulatory and market piece. I'll pass it off to my colleague Imran to round it up with our alpha plans.
Brilliant, thanks Mo. And yeah, hopefully you've all seen, I think the size of the opportunity here is huge, not just from a reduction in curtailment, but also in enabling CCS, accelerating CCS towards the vision through offshore decarbonization. Now, critical to actually unlocking this opportunity from the stakeholder engagement we did and the work that Sava and Mo just presented to you is all about that regulatory and market design construct, having that framework in place that actually enables this. And where this is unbelievably challenging is you've got CCS, hydrogen, and electricity all interplaying with each other. So to get that right is an incredibly difficult task. And that for us is what, in our view, is worth the effort, and hence why in the alpha phase, it's all about developing the analytical tools to help us understand what that optimized regime actually looks like, building more case studies in, bringing more partners on board, and doing more stakeholder engagement to truly understand what that market design could look like that brings these three together to actually unlock the huge opportunity that you kind of saw on Sava's screen and overcome some of those challenges that Mo showed. Some are in our control, some are not, but ultimately that's what our alpha phase is going to be all about. So yeah, I don't want to waste too much time. Amy, I'm going to hand over to you because I know the Q&A is where all the real benefit comes from.
Fantastic, thank you. So we've got a two-part question. So firstly, which software solutions are you utilising to optimise hydrogen use? And then secondly, do you see there being standards that all optimisation solutions should use?
So I can go first and I'll hand over to Sava afterwards. So at present, we haven't used, well, in Alpha, this is exactly what we're going to be looking at. This is the piece of work that we want to be doing, where we're looking at how you optimize not just hydrogen flows, but hydrogen, CCS, and electricity flows. I think Plexus has been kind of touted as one means and mechanism, but we don't want to go directly down that route. I think the benefit is one of our partners, NISO, is looking at that as a software option. So there could be continuity in helping to bring that into essentially BAU going forwards. But again, we don't want to lock ourselves in on that. That's something as part of Alpha, but Sava, feel free to add anything on top of that.
Quick addition. As Simran said, I don't want to be too repetitive, but yes, we are looking to use Plexus in our next studies of the project to really go in depth on this optimization. But in our discovery phase, how we identify this optimization is mainly obviously through Excel modeling. So it wasn't any external softwares we used, but it's just mainly all one big Excel model that we did our initial findings from. And yeah, but obviously now that we see that these findings, we need to go in more detail, and that's where external software will come in.
Fantastic. And does the development of hubs require any additional permitting challenges?
No, I'll definitely hand it over to you, given you read through 1,000 documents on this. Sorry.
No, of course. So I think the problem with the hubs is that it does have a lot of components, and those components are not really, the permits are not given by the same body. And so that's in there lies the challenge, right? If you're trying to do an integrated project like this, having to go through different stakeholders and different regulators is where the permitting challenge really lies, and trying to align, the timings with, say, an oil and gas permit, and also like a wind and offshore wind permit.
Well, thank you. And I see Alistair, although we sadly lost him at the beginning of the presentation, he's responded to James's question in the chat. So thank you. Next slide, please. So that wraps up the presentations for this session. Thanks to all of the projects for presenting to us today, and thank you also to those watching for any questions that you put through. As you can see from the slide, there are 6 other show and tell sessions over the next few days, so please do register for any of them that you wish to attend. The registration link's at the top of the slide, and it will also be added to the chat for you as well. Next slide, please. And if you'd like to find out anything more about the Strategic Innovation Fund, you can connect with us in all the ways set out here on the slide. There are blogs and reports you can read, our podcast series you can listen to, and also our YouTube playlist, which is where this session will be probably in the next week or so. But thank you very much. Next slide, please, for attending, and we look forward to seeing you very soon, hopefully on some of our other sessions. Thank you very much.
Thank you.
Thank you.